So we're going to keep on going with our consumer theory, analyzing the model that we have laid out in the previous lectures. To summarize that very quickly, we're studying a consumer who faces choices, who faces prices, has no control over those prices, has an income, has no control over the income, and has a utility function which represents how much she likes different bundles of goods being different relative quantities of each good. Not relative, absolute quantities of each good. And the consumer's problem is choose the best bundle, best being measured by the utility function, so higher utility is better, and choose the best utility function subject to spending no more than your income, right? So, and how much does a bundle cost? Well, a bundle costs the price of the bundle, given by that vector P, times the bundle itself, which is the quantity of each good. And we have analyzed so far, we've laid out the foundations of this model, that the consumer will choose the bundle that maximizes her utility. That is the model, I guess. And now we're going to start to analyze the predictions of that model. And we're going to start with something called comparative statics. Comparative statics are how does the output or predictions of a model change when you change the parameters. So the parameters are the things in the model that aren't chosen by an agent. They're the things that are kind of set by the outside. So here the parameters would be the quantity, the prices of goods, right? Nobody in the model is choosing the quantities, the prices. I don't know why I keep saying quantities. No one in the model is choosing the prices, so the prices are a parameter, the utility function, and the income. Those are the three things that are given to you when you start out, right? The agent doesn't choose that. And so we're interested, we as economists or students of the economy, are interested in understanding how does the output or the prediction of a model change when the parameters change. And the study of that is called comparative statics. Now, why would one be interested in this, right? Why would an economist care? Well, there's two reasons. One would be to falsify the model, right? To try to ask, does this model make sense? Is this utility function a legitimate one that's representing, to a good approximation, the actual utility of consumers, etc. Now, how would this work? Well, if the model predicts that when prices change according to this, then demand changes according to that, you could go out and you could look in the real world in your observable data set, and you could say, well, when the prices change according to this, does the corresponding demand change in the direction as predicted by the model? And so comparative statics give economists an easy tool, a very immediate way of testing the model. If your predictions, if your comparative statics don't line up with actual empirical changes when you go observe stuff in the real world, then it's unlikely that your model is a very accurate representation of what's going on. So when we say comparative statics, by the way, I often just mean the direction of the change, the sign of the change. Is it positive or negative or the same? Not how big is the change, right? Because that's a measurement question. If it goes up or goes down, that's pretty much, it's called a qualitative difference. That's pretty much an absolute thing. Whereas if it goes up by 10% instead of 11%, that's more of a measurement issue, and we're not really going to worry about it. If it's very close to zero, we're going to assume it's kind of close to zero, right? So these are empirical statistics-like questions. How much do you trust your data set? Whereas what we're interested in this class is the theoretical or top-down approach, where we just say, is the sign correct, right? Is it true that this is positive or negative? So what kind of comparative statics might we be interested in? Just some simple ones would be like, how does the consumer's welfare change when her income changes? So the welfare of a consumer is represented in our model by this thing V, right? V represents the indirect utility of the consumer, and what its interpretation is how well off in the measurement according to this utility function is this consumer under prices P and income I. So remember, the indirect utility function takes prices and income, and it returns some utility level, which is the utility of this consumer. So how does this change when we change income? If the income goes up, does the consumer get better off or worse off, etc., right? And we could have the same kind of thing with how does her income affect her demand, right? The demand given by this Walrasian demand. Right now we're talking about just Walrasian demand, not the compensated or Hicksian demand. And how does consumer demand change when prices change, right? So if I change the prices of apples, does it change the demand for pears, or does it change in demand for apples, or et cetera, right? So these are all questions that are now very easy to answer within our model. And they're easy to answer because they're just partial derivatives of some output thing, v or x star, with respect to some input thing, one of the parameters, I or p. And so this is very simple. So let's look at the simplest one there is. How does the welfare of the consumer change when income changes? The indirect utility function measures the welfare of the consumer when she maximizes her utility function according to the parameters p and I. And so when we ask, what is the change in v according when these inputs change, what we're saying is, how does the consumer's welfare change when these inputs change? And the first theorem, which is very simple, it's very intuitive, is that it's non-increasing in p. Non-increasing in p means if p goes up, welfare has to stay the same or go down. It could stay the same, but it can't go up. And most likely it goes down. It's not increasing in I, which means when I increase income, I can't be worse off. I have to do at least as well as I did before. Maybe I stay the same, but I certainly can't do any worse, right? It can't go down. And homogeneous of degree 0, if you recall, homogeneous of degree 0 means we can pull out a scalar multiple from inside. So if we multiply both p and I by some fixed amount, we get back the same utility as we had before, right? Homogeneous of degree 0 means it doesn't change at all. We can just pull them out front and it cancels. So what's that say? It says if we double prices, but at the same time we double income, you don't do better and you don't do worse. You do exactly the same. So we'll keep this lecture short, but let's look at just a quick graphical representation of how we would prove these things, right? So remember that we're not working in the real world, we're working in this model. And if we're working in a model, what that means is that we can't trust our intuitions, we have to trust the mathematics of the model, right? So we can then judge how good the model is if it accords with our intuitions. But once we fix the model, once we decide we're in a model, we have to follow the mathematics of that model. We can't follow our intuitions. Then we can judge the model based on our intuitions, okay? So what does that mean? It means that just because it's obvious that if you give someone more money, they're going to do better, right? If I give you money, you can't be, of course you're not going to be sad about it, right? This isn't money that we got from poaching an elephant or something, right? This is just money someone you found on the street. You're not going to be worse off because of this. So given that that's intuitive, but we want that to come out of the model. We don't want that to come out of our brains. So how would we show that? So this is a pretty easy one to show. Remember what our budget sets look like, right? So we have, we're actually going to show all three of these things at the same time using the same technique, and it's going to be called proof by picture. I'm just going to draw a picture. I'm not going to worry too much about it being so rigorous. So we have our axis that's bundles of, say, two goods, X and Y. So we have our X goods on the X-axis and our Y goods on the Y-axis. And if you have some income I, remember that the budget set, what is the budget set? Well, it's the triangle that's between, and we have prices P, right? So it's the triangle that lies between 2 points. On the X-axis, it lies over I divided by PX. And on the Y-axis, we have I divided by PY. And then it's just a linear trade-off between these two things. There's no change in the price if you buy more or less. It's a constant relationship between these, right? And that slope is just negative px over py is the slope of that line. And this set inside here is the budget set. Now let's think about what happens if we make I bigger. So if I think about some I prime, which is bigger than I. So if I prime is bigger than I, then these 2 points just get bigger, right? This becomes I prime over px, and this is I prime over py. And we have a new budget set. Well, what does this budget set look like? It's bigger. It contains the old budget set, right? The old budget set is still inside the new one, right? So, we have, this is the old one, and it lies inside of the new one, right? And so what that means is anything that I chose before, I could still choose now. I don't have to. You're not forcing me to, but I could choose the same bundle I was choosing before. So how could I be worse off if you've just given me more options? And that's exactly the argument here, is that if you're maximizing a function and you make the constraint weaker, you make the constraint set larger, you're going to do, the maximum of the function gets bigger. I mean, that's just a mathematical truth. That's a theorem. And so if you think about that application here, when you make the income bigger, all you're doing is making the constraint set, the budget set, larger. You're allowing this consumer to choose more things without forcing them to choose more things, right? They don't have to choose any of the new options, but they can if they want to. So you're giving them more flexibility, and this flexibility cannot be bad, right? So that's if I increases. What about if, let's just back up, and let's look at what happens if we make P less, P bigger, right? So P prime is bigger than P. That means the prices are bigger, right? Well, now we're doing exactly the opposite thing that we did before, right? We're saying that if we make P bigger, we're making the denominator of the two intercepts bigger, right? So that means we're moving towards 0. So this would be I over Px, and this would be I over Py. And they don't have to go down by the same amount now. They could go down by different amounts because P is a vector, right, not a number, so it could go down by, it could be skewed or a rotation or something. But let's just say that this is the new budget set. And notice now that this new budget set is entirely contained in the old budget set, which means I can't possibly do better because whatever I choose after the prices increase, I could have chosen before the prices increased. So by exactly the converse logic as when income increases, when prices increase, I make my constraint tighter, I make my budget set smaller, and therefore I have less options available to me, and therefore I can't do any better than I could have done before. There's no new option. I can't do anything I couldn't have done, so how could I be better off? How could I increase my utility? Now let's think about what happens if we make I and P bigger at the same time, right? So let's say we move from I to 2I, and we go from P to 2P. Well, what is 2I over 2px? It's the same as I over x. What is 2I over 2py? It's the same as I over p. Why? And so what do we get back? We get back exactly the same budget set we got before. And so of course nothing could change. You can't do better in either scenario. You haven't changed the constraint set at all. When you've doubled your prices, but you also doubled your income, you haven't changed anything about the problem, except the units in which you're measuring things, but you're not changing anything about the physical bundles in which this consumer can choose. Now, if I haven't changed the budget set, the utility is the same. That means that it's homogeneous at degree 0, right? I can just get rid of that too. I can scale my I and my P up as long as I do it at the same rate by any positive amount. So that is the first of our comparative statics. And next time we'll start to look at the more interesting cases.